Hello students, welcome back to your favorite YouTube channel, Tomachang Tutorial. Myself, Kishan Kulung, and today we are here to discuss about establishment of ideal gas equation. PV equal to nRT, ideal gas equation. Okay, before that, let us understand what ideal gas is. First, let me read the statement or the definition of ideal gas. Ideal gas, the gas which obeys Boyle's law, Charles' law, and Avogadro's law at all temperature and pressure is called ideal gas. It's very simple. The definition is very simple. We know that if any gas that obeys Boyle's law, Charles' law, and Avogadro's law, that gas is called ideal gas. The gas which obeys Boyle's law, Charles' law, and Avogadro's law, it's called ideal gas. Okay, it's very simple. Now let's begin with the main topic, establishment of ideal gas equation. Establishment of ideal gas equation. Establishment of PV equal to nRT. PV equal to nRT. This is the ideal gas equation. Now we will establish this relation. Okay. From Boyle's law, we know that from Boyle's law, we have volume is inversely proportional to its pressure at constant mass and temperature. When mass and temperature of the gas are kept constant, at that time volume of gas is inversely related to its pressure, which means if you increase the pressure, volume decreases, and if you decrease the pressure, volume increases when mass and temperature of gas are kept constant. Okay, this is Boyle's law. And from Charles' law, we have volume is directly proportional to its absolute temperature at constant mass and pressure. Constant mass and pressure. When mass of the gas and pressure of the gas are kept constant, then volume of gas is directly proportional to its absolute temperature, which means if you increase the temperature, volume of the gas will also increase, and if you decrease the temperature, volume of the gas will also decrease, but the condition should be mass and pressure should be kept constant. This is what Charles' law tells us. Okay, from Avogadro's law, we have volume is directly proportional to number of molecules of gas at constant pressure and temperature. Okay. When pressure and temperature of gas are kept constant, then at that condition, volume of gas is directly proportional to the number of molecules. We have already completed all these three laws in our previous videos. So if you want to watch that video, you can find the link below in the description. Please find that link and click on the link to watch these videos again. Okay, now let me explain this. When pressure and temperature of gas are kept constant, volume of gas is directly proportional to its number of molecules. That means if volume of gas increases, number of molecules also increases. If volume of gas decreases, then the number of molecules also decreases. Let me take an example. Suppose we have 10 liters of gas here and we have say two molecules. Okay, for example, this is just an example. We have 10 liters of gas, and in this 10 liters of gas, we have two molecules. This is just an example, not a correct one. Please take this as an example. Suppose we increase the volume of this gas and make the volume 11 liter. Okay, we have increased the volume 1 liter and the new volume of the gas is 11 liter. The number of molecules will not remain 2. Now the number of molecules will also increase. So X number of molecules is increased. So I have written 2 plus X. Means if we increase the volume of gas, number of molecules present in the gas will also increase, and if you decrease the volume of gas, number of molecules present in the gas will also decrease. From Avogadro's law, yesterday we have seen the applications of Avogadro's law in a previous video, that molar volume of any gas at STP is 22.4 liter, and we have also seen that molecular weight of any gas is equal to twice into vapor density. All these things are described in our previous video. Please find the link below in the description and watch that. Okay, let's begin our main topic, PV equal to nRT. We have seen from Boyle's law, V is inversely proportional to pressure. From Charles' law, we have seen volume is directly proportional to absolute temperature, and from Avogadro's law, we have seen volume is directly proportional to the number of molecules present in the gas. Okay, now by joint variation, combining all these three laws, by joint variation, we can write V, V and V, all these three V as a single V. Okay, this is the rule of mathematics in the chapter called variation. You can learn that there. V, V and V can be written as single V and proportion to. So we write the numbers in the numerator, the number which are in the numerator. Okay, this N and T are in the numerator and P is in the denominator. You can see this. So N and T are written in the numerator as it is. N and T are written in the numerator as it is, and this P is in the denominator, so we write P in the denominator. Okay, at this condition we should never forget to write where all parameters vary. This means nothing is constant here. Volume, number of molecules, absolute temperature and pressure, everything is variable and nothing is constant, where all parameters vary. In this condition, we see volume of gas is directly proportional to number of molecules of the gas and directly proportional to absolute temperature, but inversely proportional to its pressure. Okay, now when we replace the sign of variation with equal to sign, we need to introduce a constant. We know that V equal to, suppose I introduce a constant R here, nT upon P. This R is a variation constant. We write R is a variation constant. R equal to variation constant. Okay, this is a constant. And this variation constant is called universal gas constant. We will discuss later on. V equal to R and T upon P. We replaced this sign of variation with equal to sign and introduced R, where R is a variation constant. Okay, this R is called universal gas constant. We'll discuss this later on. Please take the screenshot of this. I'm going to erase the upper part and continue. Okay, now let us cross multiply this P with V. P into V is PV. PV equal to, P into V is PV equal to R into N into T, can be written as nRT or RNT as you wish, but generally we write nRT. Okay, R into N into T can be written as RNT or nRT. but generally we write R in the middle, so nRT, PV equal to nRT. This equation is called ideal gas equation. This equation is called ideal gas equation. Okay, this equation is called ideal gas equation, and R is called universal gas constant. R is called universal gas constant. Okay, we will deduce the value of R, or we will find the value of R later on, but first let me tell you, PV equal to nRT. This is ideal gas equation, and R is universal gas constant. Here R is called universal gas constant. Okay, any gas which follows this equation is called ideal gas equation. We have seen that the gas which follows Boyle's law, Charles' law and Avogadro's law at all temperature and pressure are called ideal gas. So this equation is the combined form of Boyle's law, Charles' law and Avogadro's law. We have seen that. So any gas which follows this equation is called ideal gas. Okay, but actually please remember, ideal gas is just a concept. Ideal gas actually does not exist, because at very high pressure and very low temperature, no gas follows this equation. No gas follows this equation. Any gas which follows this equation is called ideal gas, but no gas at high pressure and very low temperature follows this equation. This equation is valid only when pressure is low and temperature is high. Okay, so at very high pressure at very high pressure and at very low temperature, this equation is not followed by gas. So ideal gas is just a concept. Actually ideal gas does not exist. R is universal gas constant. We have seen this. Now we will find the value of R. Okay, values of R. Let us find the values of R from the equation PV equal to nRT. We have nRT equal to PV. This equation can be written as nRT equal to PV. Okay, nRT equal to PV. nRT equal to PV. We keep R in the left hand side and take this N and T to the right hand side by cross multiplication. R equal to PV by NT. NT comes to the denominator. Now at STP, standard temperature and pressure. Standard temperature, we know that standard temperature is 273 Kelvin and standard pressure is 760 mm of mercury column or 1 atmospheric pressure. Okay, at STP, for 1 mole of gas, okay, we are taking 1 mole of gas at STP. We find the value of R. First of all, I write the value of N. N is number of moles, and we have considered 1 mole of gas, so the value of N will be 1 mole. 1 mole, I hope you got this, into T. T is the absolute temperature, so standard temperature, we know that 273 Kelvin. Okay, standard temperature is how much? 273 Kelvin. And this is P. P is pressure, and we know standard pressure is 1 atmosphere. 1 atm or 760 mm of Hg. 1 atmosphere into V. V means volume. I have already told you in Avogadro's law, volume occupied by 1 mole of gas at STP is how much? 22.4 liter. Let me remind you here. 1 mole or molar volume of gas. 1 mole or molar volume of gas is equal. 1 mole of any gas at STP occupies 22.4 liter volume. Okay, 1 mole of any gas at STP occupies 22.4 liter. This was given by Avogadro's hypothesis. Okay, 1 mole of gas means molar volume of any gas at STP is 22.4 liter. So we have taken 1 mole of gas. That means volume of 1 mole of gas, okay, volume of 1 mole of gas at STP is how much? 22.4 liter. I hope you got this. Now, by calculating 22.4 and 273 by simple division, we get 0.082, okay. This ATM and liter both are in the numerator, so we write ATM liter, okay. Let me write in the full form, LITRE liter. See, this mole, MOLE mole, this mole was in the denominator. When we bring to the numerator, the sign of the power changes. Now this mole has the power +1 here, so when we bring to the numerator, this +1 changes to -1, so it becomes MOL to the power -1. So 273 is already divided with 22.4 and we got the result 0.082. Now this Kelvin has power +1, okay, +1. And when we bring this Kelvin to the numerator, what happens is this plus power changes to negative, okay. That means Kelvin becomes -1. So the value of R is 0.082 ATM liter per mole per Kelvin. Please remember this value because R is universal gas constant and the value of R never changes, okay. Another value of R is, this is another one. You need to remember this also. Another value of R is 8.314 joules per mole per Kelvin, okay. You need to remember this also. Okay, this was for today. I hope you understood the concept, what I try to teach you. Thank you so much for watching the video, and hey, please don't forget to subscribe and click on the bell icon to get more video uploads. Thank you.